workshop is coordinated between two European projects. One project, DILAPRO, I will let Ricardo, the coordinator of the project, speak a little bit more about. And also another project called FLASH. And Gaetano is connected from Italy. He could not make the trip, but he's connected. Are you here, Gaetano? Okay, thank you so much. So this workshop is aiming to let's say promote this kind of new developments we have been doing within these two projects, and also to show you it's kind of premiere, because these projects are now 2 years and a few months that they will last will end at the end of 2026, and these new results are really quite kind of say new and will be shared with you as a first public view here what is going on with this kind of project. These two projects, the first one, as I said, digital twin, the DILAPRO is mainly dedicated to digital twin use for the control systems in additive manufacturing, maybe laser power bed and direct energy deposition bed, but also it's not only dealing with the control system, but it's also the certification system that is implemented in one component which will deliver at the end of the project. For laser, I will let Gaetano speak more, but after that, Anna gives some, let's say, a few words about the organization of this workshop and how it will be run.
DILAPRO stands for Digital Laser Production, so it's digital twins laser processing, multi-capability manufacturing of complex components and certification. So this is a European project composed by 4 SMEs, 1 large industry, 3 RTOs, 2 universities and 1 association. Some of the logos are familiar to you, so we have DTI, we have EWF, this European Welding Federation, the University of Dublin, BTU, also in Denmark, CRM, FilmMate, that is in Norway, INDEA, that is in Spain, Prima Digitalisation, that now changed the name, is Outform, Petit Qualified AM from Germany, and Amquam from Switzerland. So what is the main focus of DILAPRO? We want to enable fast implementation of complex products, manufacturing to ensure that complex products created by laser technologies, and I will introduce later these technologies, met all the industry needs in terms of design, quality, costs, and also sustainability. So, in a nutshell, we use 3 main technologies, PVF, DAD, and also laser texturing. And for these 3 technologies, we use also 3 main materials. 1 steel alloy and 2 Inconel alloys. So when we start this project and we start to write the proposal of this project, we realize that we have some problems related to AM and also certification. So we have a lot of certification bottlenecks, and these will translate in slow certification cycles, in the production scalability, and cost efficiency, and also complex and manual process that we want to avoid. That's why we try to digitalize all this process, and also resource intensity. So we thought that the traditional AM certification is time-consuming, is costly, and is heavily reliant on manual or quality checks. So the idea behind DILAPRO is to have 2 platforms. DILAFACT, that Ricardo will explain later better with more deep what is going on this platform, that is more related to the digital twins, and also DILACERT, that is more related to the certification of these components produced by AM. So, in a very nutshell, we can say that digital laser factory, DILAFACT, enable data-driven production decisions to enhance efficiency, sustainability, and also quality. And the key functions of this platform is a digital twin, in-situ monitoring, and real-time adjustments for laser-based additive manufacturing. In the other hand, the DILACERT is streamlining and transforming the certification process for additive manufacturing parts. So this DILACERT aims to replace the manual, the heavy documentation that we have nowadays in this process to a semi-automated data-driven process. And this is our idea with this project. So we'll combine FACT and DILACERT to have these digital twins and real-time monitoring for quality assurance in a continuous way.
My name is Patrini. I'm the Innovation and Intellectual Property Manager at Outform. Here we present the FLASH project where I'm the coordinator. In particular, the FLASH project is composed by a consortium of 17 partners. We started the project in January 2024. We are almost at the end because the project will be ended at the end of this year. And here you can see all the partners within the consortium. Basically, the FLASH project is about a novel concept of a very interesting machine. Basically, the FLASH project will launch the next generation of the laser machine that will be based on 4 key technology developments. First of all, there will be the integration of 3 different laser sources, 3 beam inside a single one machine. There will be also dynamic beam shaping, and improved in process monitoring and control, and also a part dedicated to the process design for laser-based manufacturing. So here you see all the actors and all the partners where they are contributing to the different let's say development of the project. But starting from the very basic of the project and the development that we have, basically we base everything on our multi-process laser machine. So it's our Zenith laser cell, where we basically we are trying to integrate and implement all the project results within this machine. So here you can see very briefly the schematic of the solution, where what we are trying to integrate within this machine: 3 different laser head, a coaxial gas access nozzle, the galvo scanner, and a water jet guided nozzle. All of that is, as you can see, with 3 different lasers, 1 infrared and 2 green. This, of course, in order to develop and to produce all the use cases that are implemented in the project. FLASH also will apply this innovative 3D dynamic beam shaping with an adaptive energy distribution in response to the changing process condition, in order to deliver improvements in the product quality and process efficiency. Then also we have an important part considering all processes and parameters available to the FLASH machine platform, because the process design mode will identify the best sequence of individual processing steps and provide optimized parameters for each of the solution. Here we we have very briefly the different use case that will be produced within the project. We have, as you can see, several use cases from very different sectors. From the medical sector, we have the orthopedic implant. The most interesting one, of course, for you will be the ones on advanced tooling. So we have these 2 different use cases on polycrystalline diamond microdrilling and CDM grinding wheels. We have also the automotive case studies for cross-cutting welding, and also the copper head stripping and welding typically used for electric motors. Okay, so basically here a recap use case that we are developing. As you can see, in particular for the polycrystalline diamond microdiscs, we are trying to reduce the material waste by up to 20%. And for the grinding wheels, we are trying to eliminate the polluting chemicals used in the galvanic electroplating process, reducing the process waste by 30% and extending also the tool lifetime by 3 times. In particular, let's say, moving to the experimental process development, we are developing some experimental laser machining process for the CVN grinding wheels, and our primary focus here is creating a square abrasive seats and chip flow path to improve the tool performance. As you can see here in the center images, we have successfully drilled 2 holes square geometries using a multi-pass laser strategy. We utilized a 2 kilowatt laser with armor shielding to achieve clean and drilled results, and it's followed by a grid blast to refine the edges. To the right, you will see our preliminary results for the water jet guided laser, and by using a 100 micron nozzle at 10 kilohertz, we can create some precise channels even in randomly oriented abrasive surfaces. This structure is critical for managing heat and degree during the high intensity grinding. Then here for the polycrystalline diamond, let's see, as you can see here, the focus is on water jet guided laser turning for PCT micro drills. Here our objective is to take stock diameters of 3 to 4 to 5 millimeters and turn them down to a final diameter of less than 0.5 millimeters. The process is split into 2 steps: the linear cutting, you can see here, in order to remove, let's say, basically the bulk material, followed by the synchronous rotation to refine the geometry. We achieved the final surface roughness of less than 1 micron within a 30-minute processing window. If you look at the material removal rate motor plot, we have optimized our parameters at 65.8% of 190 bar of pressure, and this ensures we maintain high productivity while achieving the smooth surface finish visible in the semi images on the right. And then also for this use case, we look at short pulse 3D micro machining for complex drill features like flutes and face geometries. And our research shows that power selection is a trade-off. 12 watt is recommended for a maximum material removal rate, while the 8 watt is needed for superior surface finish. The graphs on the right, as you can see here, illustrate the influence of pulse energy and beam velocity on the PCT ablation. We identified an ablation threshold and found that at 24 microjoules per pulse we can maintain a stable surface finish even as we increase beam velocity. And this strategy allows us to precisely machine 1.5 millimeters PCD into the functional micro drills shown here, with specific for basic removal path designed for both the flutes and the cutting phases. So basically here are the most, let's say, interesting, important results that we have on these particular use cases. And at the moment we are finalizing the machine solution. Here you can see the status of the machine at the moment. Basically we have integrated new features, in particular this new autonomous 6-axis robot, plus a rototilt table, so for the 8-axis control, and also we achieved the accuracy of less than 10 microns and minus less than 5 microns for the repeatability. And also we have a very smooth, very fast head swap within 15 seconds in order to change from one process.
Hi, hello everyone. My name is Riccardo Tonello. I'm a consultant and technical project manager at the Danish Technological Institute in Denmark. And today I will discuss a little bit about this project, but more specifically for the DILAFACT software, which stands for Digital Laser Factory. I actually have a small agenda, so just to present a little bit what are the challenges in advanced manufacturing, what means also the digital twin integration for the quality assurance and quality control, and then more specifically on the tool, DILAFACT. So in advanced manufacturing, especially in additive manufacturing, there are different steps to, in a way, achieve the final component. It starts from a decision process and goes from the design to the validation of the product with the quality assurance and quality control. But of course, there are several limitations. First of all, the materials that we can use are limited. Also, there are some requirements on the post-processing. It's also a bit difficult sometimes to scale the products or technologies, and of course, the design complexity. Among those, the quality control, of course, is quite an important part. And yeah, some of the failures that we can see, for example, in some of the processes are related in different steps. For example, the deep failures, qualification failures, or even the field failures. So when actually the part has been already delivered to the customer. So among all these things, of course, there are a lot of challenges that also Anna discussed before, about the quality checks and yeah, all the certification bottlenecks and cycles that hinder in a way the full development of this technology, and also the required steps for the parts. So this is traditionally what we do for some, we print also some coupons along with the parts to test if everything is okay. And also we inspect ideally the process while printing. So as you can see, there are a lot of different steps. And ideally the integration of data analytics, machine learning, digital twin can in a way help this process to in a way strengthen this quality assurance and quality control, having a better, also a faster certification in a way. So to integrate the digital twin, of course, there are different steps of how the digital world works. So there is the digital model, there is the digital shadow, which is basically just simulating the process. But when we talk really about digital twin, is also how to in real time adjust the parameters on fly in a way. So for this, in this case, the digital twin that we would like to achieve, and we are trying to achieve, is basically comes from the combination of all these factors, from the multi-physics simulations, from the data, but also the characterization. And of course, to even go further on this slope, we would like to understand what has happened, but also what will happen and how to actually make it happen. So in a way, all these considerations will optimize this digital twin. So yeah, the DILAPRO is basically, as Anna also mentioned, is divided into two different pieces of software. The first one is the DILAFACT software, which is mainly on the quality assurance, and the DILACERT software, which stands for Digital Laser Certification, is links basically the quality to the different standards. Yes, so in a nutshell, is about indeed like having this combination of data from the sensing and data from the simulation, combine them in the digital twinning way to be able to have quality, but also in couple it with the in-situ monitoring and real-time adjustments. So yeah, that's basically concept of a hybrid digital twin, and of course all this output will be fed later on in the digital laser certification of DLSR software to, in a way, assure the certification. So yeah, as I said, it's partially divided into the simulation-based digital twin and the data-based digital twin. And we have created the software divided into modules, starting from the multi-laser processing. So in this case, to understand when to use which laser to do what. And then, of course, have a module about the quality to assure if the quality is okay, is enough to advance to the next step. And then also a validation step that is basically just prepare the stage for the DLSR software later on. And ideally, the software should be used by different users. So of course, there will be different admin rights in a way. Yes, as also before mentioned, we are using 3 different technologies. We have the powder bed fusion laser bay, we have the direct energy deposition, and we have the laser surface texturing with 3 materials, Inconel 625 and 718 and 316L stainless steel. For the software, we are using the suite from Petit, which is this company in Belgium, which basically a partner mainly data analytics and interpreting data for these uses. So starting from the first part, which I would consider as more related to the simulation-based digital twin, we are using different things to prepare to create this digital twin. We are using this Global 3800 system, which is basically a physical simulation. In this case, works. So it's basically the part, the sample is heated up and runs quite continuously and rapidly, so that can simulate the frequency of the additive manufacturing. We have the scouting of different simulation tools to understand, of course, the best performance tool and what is needed to achieve and detect effects. And also we have the analysis of and testing of coupons on tensile test and torsion test and other type of tests. So related to the simulation test, we analyzed the 32 different modeling tools to create some raw maps and identify the best ones in terms of best performance of accuracy, best computational time, and also ease to use. And then we, of course, to scale a little bit towards the actually prescriptive analysis or analytics, then we have we started identify some key research topic, and one of these is the process identification using this physics-inspired machine learning to understand the presence of defects. We also do the segmentation of particles using microtomography images, and also the deep learning-based prediction of the microstructure and evolution to, in a way, describe also how the process works. And later, as a final step, also the generative AI models to fine-tuning for the surface surface texture prediction. As a second step, the quality model that I would more consider as a database digital twin, we have different sensors. We have the thermal emissions. We have the optical images sensing. In this case, is basically kind of images that are in a way analyzed, and all the effects can be detected. and predicted. We have also some acoustic emission sensors and electric magnetic signal, such as the eddy current sensors. Perhaps Bernard will talk about that later. So in this case, the idea indeed is to have the data acquisition, to have the processing of this data, to also explore some algorithms, and then create this real-time feedback loop. And here is the quality model, so we can basically select which sensor we have and what we would like to predict. And then we have all this output that can, in a way, guide us on the best manufacturing process. And later on, as a not less important part, is also the cost calculator. So we had the analysis on the sustainability and the carbon footprint of the processes. And we can also, in a way, select which is the best process, which material. Yes, so in this case, this part, as I said before, prepares a little bit the ground floor for the second step, which is the DILASERT software. And the DILASERT software, in a way, combines or connects all the quality with the related standard. And of course, the word of the standards is pretty big, so what we are focusing is just a small bit of it, which is related to the advanced manufacturing processes. There's that. Yes, so just to finalize, so the impact of this project can comprehend manufacturers, engineers, and regulators in different ways. To, of course, have these bigger ecosystems about faster delivery, high quality, and certified products.
Hello everyone, my name is Bernard Rova. I am very glad to be part of DILAPRO. In this project, you saw that quality control, quality management is a key deliverable, and there will be digital tools that will be developed to make sure we can deliver quality. So with our contribution to the project is a very thin slice in the quality management, which is at the end of the process, which is called non-destructive testing, that you all know. And that provides, let's say, a final view over possible defects that you may have in your part. So this is what how we are contributing to the project, and I will show you now the development we did in terms of technology, hardware and software that is integrated in the machines, and then the interfaces towards the quality management system that Ricardo just described. So our company is based in Geneva, and maybe this is not a good presentation.
Yeah, it's the presentation of yesterday.
This is presentation of yesterday.
Yes.
Can you open the other one?
Yeah.
It's just, so I will start. Non-destructive testing is not very sexy, I have to say. We discussed yesterday about the unions coming to you and asking about recommendation for a job, right? And non-destructive testing is definitely not in the top list. However, as you all know, because you're in the material science and industry, this is absolutely a critical step into providing, delivering safe infrastructures, safe transportation systems. And, you know, for instance, in the plane you may take tomorrow.
No. Yes.
Try the other one.
It is called workshop. The title of workshop. So, it is, and it is a very well-functioning industry. If you look at the failure in the aircraft transportation industry, actually a very small number of events which are related to a, let's say, failure of the process in non-destructive testing. As you know, this is a statistical process, so there is a 10-9. the 10⁻⁹ statistics in the probability that the failure happens. So it is calculated, it is there, and our job, because I'm myself an inspector as well, so our job is to make sure we follow certain codes and standards and deliver the proper inspection. But it is absolutely, I would say, working very well across aviation, energy, transportation, and we can discuss how to, this industry has to progress. So in this project, we do something slightly different, starting from this plot that I present here about the future of non-destructive testing. Non-destructive testing has 4 issues. Number 1, limited inspector availability, because our missions, we not let them go to the non-destructive testing industry. This is the most fascinating and extraordinary job. Actually, we lack inspectors. It's not so well paid. It's a profession that's not very attractive. And in Europe, we lack now inspectors. On the other hand, people want safer and safer infrastructure, risk adverse, right? All the engineers in this room will make more complex systems, more complex designs, which require advanced NDT, and then the economics of NDT as well. We cannot; it's not unlimited funding, so there are strict budget limitations. And all together makes not me. It's not me talking now. Small company in Switzerland. These are these big guys here. For instance, the European Agency for Safety of Aviation. They consider that something has to move with non-destructive testing. And this is related to in-situ inspections, exactly what I'm going to present today. How can we integrate non-destructive testing early in the manufacturing process? And also new data processing. So new data processing is things related to machine learning, advanced processing. I don't want to name it, like artificial intelligence. Mostly like machine learning. So in this project, sorry, keep going back. So in this project, what we are basically doing is integrating compliant non-destructive testing systems. So this is slightly different from monitoring. Monitoring is whatever helps you make a more stable, reproducible process. And non-destructive testing is a standardized technique that gives you information about defects in your part. And so we develop non-destructive testing systems for various advanced manufacturing industries. So the one we developed in DILAPRO is for laser-powered fusion. So you have here a machine on which we installed our non-destructive testing system. We apply as well in DD, direct energy deposition. And in collaboration with Ariane 6 and ESA, we deploy also our technology for this beautiful part. These are the cryogenic tanks for Ariane 6. And as you know, the rocket is basically just tanks, right? 90% of the volume is tanks. So these are hydrogen and oxygen tanks. And in this project, we developed same concept. During the forming of these aluminum parts, these beautiful technologies, friction stir welding and shot cleaning, to create these cylinders, we perform non-destructive testing to detect cracks that may be caused by damaged bolts. So this is what we are doing. One word about the NDT technique we are using. It's eddy current. Why? Because it's very robust. It provides surface information. And if you deposit your material layer by layer, actually you always have some surface that you can inspect. And at the end of the process, you may reconstruct your 3D model based on this non-destructive testing data. It works non-contact. It has a lot of standards. So in this project, we don't invent new standards. We use a rich corpus of standards in various industries. And it's robust equipment that can be integrated in what it calls a hostile environment. So the idea is that the sensor is a coil. The sensor travels with the recorder, which is spreading a fresh powder bed. And the sensor can measure the consolidated part of the build plate, which is the metal part that has been melted and resolidified. And it measures that in, let's say, the cold state, so after the melting has been done. And the system is able to detect a variety of features. And the good point is that, again, it's not me telling you what the system can detect. This is already well described in the standard. Of course, discontinuity is cracks. You know eddy current because it detects cracks near the surface or at the surface breaking. But also you may measure certain geometrical properties. You may measure metallurgical or mechanical properties of the product. As you know, in aluminium, eddy currents are used to sort products in the aviation applications. And of course, the physical properties, conductivity and permeability, and potentially also residual stress. And again, this is not me saying, oh, I will do all these sort of things. This is the code and standard saying, you may do that provided that you have the proper equipment. So two machines here where our system is deployed. The first one I showed before is a Nikon SLM machine, and this one is EOS 290, and these two systems are used in the frame of DILAPRO. Something special about our equipment is that we designed the hardware down to the smallest bits of it, which are here this integrated circuit. So we have proprietary ASICs that we deploy in this system. And this makes like a competitive advantage over our competitors, because as you know, there are a lot of eddy current companies providing the equipment, but they have issues at doing this sort of integration, like putting the system on the recorder, or having like small cables, or let's say miniaturization and parallelization is not easy with standard equipment. This is our differentiator. Now, I will show what we can detect. So we are in a system where you deposit a new layer of material in order to detect defects on the surface. So I will show you here the ultimate detectability that we have with our technology. So this is for the RN6 project. So this is a casted aluminum part. We have defects here from 0.8 to 0.1 millimeter, and we detect easily down to 0.1 millimeter surface breaking defects. Now, in the context of additive manufacturing, this is a bit more complicated because you have process variations, you have variation of the microstructure in your part, so it makes it a bit more difficult. However, we can demonstrate that we detect subsurface features. So this part here, these dots that you see here, are defects which are located below the surface. And this is the critical advantage, and I will conclude with that. With this system, you can detect defects that are below the metallic surface. And this is not easily accessible within a machine today. This is something that will require ultrasonics, for instance, but we don't know how to put ultrasonics inside the machine, or of course, X-rays and so on. This is not to be considered. So we detect subsurface feature, and we deploy this technology now in the machines, so that during the fabrication we can detect defect and provide this information for corrective actions, for preparing the part certification, or just to stop the process if these defects will not be possible to repair them by post-process heating.